So we concluded last time by looking at divisors and algebraic submanifolds of CPN and how these two also interact with line bundles. Today we will continue, let's say, our applications of what we learned with this sheaf cohomology and check cohomology. And just one quick thing I want you to notice, which again we said it before, is that but we never proved it, now we can, is that the Rhur cohomology of M, it's isomorphic to the sheaf cohomology of M, where the sheaf is the sheaf of locally constant functions, real locally constant functions. And why is that true? Well, this is because of the abstract Rhur theorem and the fact that this sequence of sheaves, so here we have, again, locally constant functions, just embedded into smooth functions. Then you take the differential to go to one forms, and of course the kernel is precisely the locally constant functions. And then you go to two forms again with the differential, etc., etc. This is an acyclic resolution. It is an acyclic resolution by the first theorem we saw yesterday, which said that if you have a sheaf of C infinity M modules, then it is acyclic. So each one of this, right, besides Rm, is in fact sheaf of C infinity M modules. Therefore, this is an acyclic resolution. And then we know from the abstract Rhur theorem is that the cohomology of the global sections of this resolution is precisely the sheaf cohomology of this first object here. So on one side, we have the sheaf cohomology of Rm, so locally constant functions. And on the other side, we have the cohomology of the cohomological complex given by global sections of these sheaves, but that's nothing but the Rhur complex. Okay, so we get the Rhur. Any questions about this theorem?
No, that's okay. Good.
So now we want to talk a bit about what you can do with complex manifolds. This is a more extensive topic. I think perhaps this should have covered at the beginning when we were covering manifolds in general. But I felt I was not gonna really use it in this course. But now I think it's, since we do have the time, it's worth having a look at it. And all of this is to define the Dolbeault cohomology of a complex manifold. So we'll start with a complex manifold. And given a point in M, then TPM is of course a complex vector space. Of complex dimension M, complex dimension N, where N is the dimension of the manifold, the complex dimension of the manifold. Also, of course, it is a real vector space. Of real dimension to N. Okay. So one thing we can consider is the complexification of this real vector space So this, okay, let's stop here for a second because we want to consider this. So we think of TPM now just as some real vector space. And you take this tensor with C. So this is the complexification of a real vector space. You can completely forget for now that this is a complex vector space, yeah? So this is now a complex vector space of complex dimension to N. And maybe just one small observation. You see here we're tensoring over R. If we were tensoring over C, then it means that we know that this is a complex vector space, and this would just be doing nothing. Yeah. So tensoring a complex vector space over C with C just does nothing. But the interesting thing here is that on TPM, if you kind of remember that it's a complex vector space, you have a map which is induced by multiplication by I. So equipped with double P, equipped with the operator J, usually called J, from TPCM to TPCM. So J is the multiplication by I in TPM, and then we extend it, extended by linearity, by C linearity to TPC. Okay, so this is a bit subtle, I would say. It's like, oh, but why don't you just put I? Why do you call it J? Why don't you just say, why do you say J of V and not I times V? It's because this is, yes, this TPM is a complex vector space, but just think this multiplication by I as a linear map, as a real linear map from TPM to TPM, and call it J. Then every time you have a complexification, you can also complexify the real linear maps, that is J, and this is our J on TPCM, okay? So this is one kind of multiplication by I. The other kind of multiplication by I, of course, is the one coming from the fact that it's a complex vector space, so we can regularly multiply by I, and that we'll just call multiplication by I. One property of J, of course, an important property of J is that if you apply it twice, you get negative identity. And now we can separate this complex vector space into two parts. This is the 1, 0 part, which is V minus I JV in TPCM, such that V is in TPM. And then we have the so-called 0, 1 part, which is V plus I JV in TPCM, such that V is in TPM. Okay, and again, this J represents multiplication by I in TPM, and this I represents multiplication by J in by I, sorry, of course, in TPCM. Okay, so these are two different things. And why are these two spaces important for any reason? Why do we consider this in particular? And the observation is that if you apply J to an element of the first space, you get J of V. Remember that J is C-linear because we extended it that way. So minus I J squared of V. So this becomes -1, and this becomes just JV. So this is nothing but I times V minus IJV. Okay, so this is IV is this term here, and IJV is this term here times I divided by I. And if you do the same for the other part, the 0, 1 part, you see that you get JV plus I J squared V, and then you get almost the same, but it's negative I times V plus I J V. So in principle, what we're saying is that T10 PM is the eigenspace of eigenvalue I for J, and T 0, 1 PM is the eigenspace of eigenvalue -1, negative I for J. Okay, so they have some kind of intrinsic meaning. Okay, it's not just this V minus IJV. What is this? This implication, of course, is not complete in the sense that this proves only that T10M, for instance, is contained in this eigenspace. Then you would need to prove, of course, that it's a derived dimension, but we'll skip that. Of course, the idea is to use the fact that here we take all V in TPM, and you have to prove that somehow this is injective. It's not too hard. So this image is the complex dimension N, and therefore it's they both have dimension N, so together they form everything. So these are precisely the eigenspaces.
Two questions. One second to the definition of J. If we consider the TPM as a real vector space, does that mean that multiplication by I is just a permutation of the base elements, so to say?
I'm thinking. Think so. Yeah, should be. Yeah.
Okay, then
yes.
Then I understand what J does. Okay.
Okay.
And you the last argument I didn't quite grasp.
The last argument it's sketched in the sense that, I mean, here I said implication. So we saw this. That if you apply J to an element of T10, you get that this is an eigenvector with eigenvalue I.
Yeah.
And the same for negative I. So I claim that this is exactly the eigenspace, right? This is, I mean, but just from this is not immediate. This just means that it's contained in the eigenspace, right? I mean, every element of T10 is in the eigenspace. Is it really the whole eigenspace? Yes, because this actually has complex dimension N, and this is also complex dimension N. Why do they? Maybe there is an easier argument. Yeah, maybe from here you can see that the eigenvalues of J, they're precisely 2, and they are I and negative I.
Yeah.
Right. And so they must form everything, and these two also form everything. Okay, maybe that's not so obvious as well.
No, I thought you said something like they were orthogonal or something, but the two spaces don't construct the whole space, do they?
They do.
They do. Okay.
Yeah, because I mean, first of all, there are two eigenspaces for different eigenvalues, so they're disjoint. I mean, disjoint. They intersect only at one point, right? They intersect only at 0, and the claim is that they actually have both dimension N.
Oh yeah. Okay.
Right.
Good. Then.
So I mean, you can show this in different ways. For instance, you can say that the map that sends V to V minus IJV is injective, and here we have complex dimension N. So, this makes sense. So this is complex dimension N. If this is injective, then this is dimension N. So you're done. You can find, I don't know, maybe a bijection between the two, a linear bijection between the two. So you know that they have the same dimension, and then this dimension must be N. Things like this.
Yeah.
I think there are many different ways to prove it. I just don't want to prove it.
No, I'm good now. Thank you.
And the standard thing to do here is to identify. We identify TPM with T10 via the map that sends V to V minus IJV. This is the standard thing to do. And then we define the bundle of PQ forms. So lambda PQM as the tensor product of T10M star, wedge T10M star, and this is for P times. And then you do the same with T01 Q times. Oof, this P is bad. Let's say at a point, maybe we can actually forget the point now, because this is really a bundle. and D0, 1, M star. And here we have Q times. Okay, so this is the so-called bundle of PQ forms. And maybe to get an idea of what is this. So a section of lambda PQM is given locally. So what does this look like in local coordinates? By a linear combination and linear, this can be by a infinity M linear. Yeah, so a smooth section. So the coefficients are smooth functions. That's what I'm trying to say. By a infinity linear combination of elements of this form. Elements of the form DZI1 wedge 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 DZIP wedge DZ bar J1 DZ bar GQ, where of course DZI1, I mean DZI is DXI plus I DYI, and maybe I, it's a bad choice here, and the J bar is DXJ minus I. Yeah. So you should think of this DZ as the image of DX under this map, basically. If it makes sense, no? Because DX here, if you multiply it by I, is sent to DY, I think. No? And so when you play this map, you get DX minus I dy. So maybe it's this one.
Yeah.
Okay.
Yeah.
And so the idea is that you want to separate basically what looks holomorphic and what looks anti-holomorphic. Anti-holomorphic meaning that the bar of it is holomorphic. Okay. And there is a reason for this. Is that now if you take the differential, so let's just take a simple form, the simplest form possible. So sorry. You take a form omega equal f dz1 wedge 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 dzp wedge dz1 bar wedge wedge dzq bar, where f is just some smooth function. Okay, I'm not going to make the, let's say, on some open set u. Then let's try to compute the differential. So basically what you get is the sum from I equal 1 to n of the f dzi, dzi wedge dz1 wedge 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 dzp. Of course, if I is one of the first p, this actually becomes 0. Plus, again, the sum from I equal 1 to n of df in dzi bar. And this is just local coordinates. So this dzi and dzi bar, these derivatives are really the standard derivatives in Cn. And then you have dzi bar, wedge, dz1, wedge, dzq. Okay. And okay, this is not the definition, right? This is not the definition of the differential or something like this. You would actually have to do this with x and y, but you can prove that, I mean, this is just a linear change of coordinates. So it turns out that this is the same as the usual differential. And now it kind of makes sense to give a name to these operators. Maybe we can call this the delta of omega, and we can call this the delta bar of omega. No, it kind of makes sense. They're really two separate things. In particular, oh, I made a mistake. Sorry. Of course, you don't just forget everything else. This doesn't make sense. You have to put everything. Oh. dz1 bar, wedge dzq bar, and here you have the first one is dz, yeah, and then you have dz1 bar, dzq bar. Okay, sorry. And this we call delta omega, and this we call delta bar omega. So yeah, why do we call them like this? Well, because they're kind of really separate. If you look at this, we started with something which is of it's a PQ form. So this is what we call a PQ form, which is, by the way, a P plus Q form, right? In the standard RAM sense, this is just P plus Q degree, but we call it P comma Q. And when you apply this differential, you get two terms. So one which is a P plus 1 Q, and the other one is P comma Q plus 1, right? And since the d squared is equal to 0, you actually get this is equal to 0, and this is equal to 0. There is like a small composition to do here, but we'll not do it. Just believe me. Or, maybe try to do it yourself. But there is a problem here. So problem. This delta of del is usually called del, this operator. Del of omega is well defined only locally. What I mean by this is that, okay, if you have a local expression, you can take this del and you get this object. But what happens if you change coordinates? The usual. In fact, if you take, let's say, the del of some omega alpha, so some local expression, this should be the del of some g alpha beta omega beta. And this g alpha beta would be the transition functions of the bundle of PQ forms. Yeah. But then this becomes, okay, by the usual rules, del g alpha beta times omega beta plus, sorry, no, this is an equal. Plus g alpha beta del omega beta. And in principle, we would love this to be, so question, is this equal to g alpha beta de omega beta? So do they glue back together, no? Because we want to define this del of omega. And here we have del omega alpha, and we would like this to be the same as g alpha beta times del omega beta. So do they glue together? And the question is basically no, because this is non-zero. So they don't glue because in general, we cannot really ask this derivative is 0. This is a holomorphic function. You apply its derivative, and this is just something. Instead, if you do the same game for del bar, then we're actually very happy, because these are the transition functions of our holomorphic bundle. So del bar is 0. Yeah, this is equal to 0. In particular, they glue. Yeah. And this operator, this del bar operator, is not just defined in an open set, or not even any open set in a coordinate chart like this del bar, like this del is, but this del bar is really defined everywhere on a complex manifold. And in particular, it sends PQ form to P comma Q plus 1 forms. And it satisfied the property that this del bar squared is 0. So we have a cohomological complex. And what is this cohomological complex? Well, we need to fix P. So for each fixed P. And the first thing we put here is actually P0 forms, which are holomorphic. So holomorphic P0 forms. So things which locally look like F, DZ1, DZP for F holomorphic. Okay, so linear combinations where the leading factor is not just smooth function, but it's actually holomorphic. And we embed this into smooth P0 forms. And now we can take our del bar. And if you take the del bar of such thing, you get something which is P1. And then you take the del bar again, and you get P2, etc., etc. Okay. So this is now a cohomological complex. And the one that is usually considered is the one for P equals 0. And we call it HQ del bar M, be the cohomology of this complex for P equals 0. And this is the Dolbeault cohomology. This is the how do you spell this? Dolbeault. Cohomology of M. Okay, so let's slow down for a second again. So maybe let's go back a few steps. Let's repeat everything. Okay, we have a complex manifold. We can define this operator J, which lets us divide the space into two parts, T10, T01. We use this to define what are PQ forms. Okay, so our sections of this bundle, and they locally look like this. Then we observe that if you take the differential of a PQ form, which observe that this thing is a subset of simply n P plus Q forms. Yeah. So every n form can be decomposed as a sum of PQ forms for every P and Q such that P plus Q is equal n. You can just separate all of this. And if you apply the differential, the standard differential to one of these forms, we notice that this is kind of naturally divided into two. So this delta and this delta bar, but this delta is a bit fake in the sense that it only works locally. Well, this delta bar is actually a well-defined global operator on M. And since it comes from the differential, it satisfies del bar squared equals 0. Therefore, there is a cohomology associated to it. And we call this cohomology. So for every P, there is a cohomology. And when we take P equals 0, this cohomology, we call it the Dolbeault cohomology. Okay, any questions?
No, that's good.
Okay. So observation, of course, is that all of these things, so C, M, infinity, 0Q, are sheaves of C infinity M modules. right? You can always multiply by smooth functions. So they are acyclic. Yeah, for p greater than or equal than 1. Therefore, the cohomology of this complex, so the Dolbeault cohomology, is nothing but the sheaf cohomology of the first factor. So the theorem, all of these observations imply the theorem that the qth cohomology of the first factor, so this would be OM00, taking p equals 0, and OM00 just the holomorphic functions, is isomorphic to the Dolbeault cohomology of the manifold. This is again abstract Durand theorem. Okay. There's an important lemma here, which we'll not prove. So remember, we proved that every time you have a star-like open set, then it's the RAM cohomology is 0. And this is also true for this Dolbeault cohomology. This is the Poincaré-Grothendieck lemma. So we take U in Cn, star-like, open set. Then its Dolbeault cohomology is 0 for every q greater than 0. Okay, so what we're saying, I mean, what the Poincaré lemma, so the one with the standard RAM cohomology, tells you that local, I mean, in a star-like set, we always have primitives. And here we're saying the same, but now primitives only means del bar primitives. Okay. The technique still involves some integration, just like in the Poincaré lemma, but this integration needs to be literally complex. Okay, so you have to make sure that the del bar of this object is 0. So this del bar is actually very important operator, and so maybe just a small excursus in orange. One standard thing to do is solve equations of the form del bar of f equal u for u given. Something like this is very standard to say. Okay, so you're given a u and you want to solve del bar of f equal u, maybe with some boundary conditions as well. Okay, so maybe you want to do this in some open set and you ask that this f has some values at the boundary as well. So, you know, standard things you would do in a differential equations case, and this is somewhat a geometrical meaning to this differential equation, is that this is a del bar. Okay, so now using this Grothendieck lemma and this fact that we know, for instance, we observe that since Cn is star-like, of course, its Dolbeault cohomology is 0. For q greater or equal than 1. Of course, its Dolbeault cohomology of level 0 is, and I'm gonna wait the answer from you.
What was the question?
What is the 0th Dolbeault cohomology of Cn?
Probably.
So remember, the 0th Dolbeault cohomology is the kernel of this first delta, right?
Yeah. But what does delta do?
Del bar takes the, so I mean, just take p equals 0, right? So this is just a smooth functions. And you're asking which smooth functions are such that their del bar is equal to 0. Remembering that del bar means taking this anti-holomorphic derivative. So basically we're asking which functions f are such that this derivative is equal to 0.
Okay. But we're only working on holomorphic functions, or
No, the functions are smooth, right?
okay.
And
But
we ask
the
about which ones of the smooth ones are such that this derivative is zero.
are those the holomorphic ones, or
Exactly.
yeah, okay.
Exactly. Which we also saw here. So if you take q equals 0 here, you get the 0th cohomology of the sheaf of holomorphic functions, which we know is old global sections, right? So maybe I'll write it here. H0 del bar of Cn is simply all holomorphic functions, functions on Cn. Okay.
Yeah.
This is true for any manifold, actually. We don't need star like or anything. So, okay, this we know from the Poincaré growth-index lemma, and this in particular implies by this isomorphism that we saw here that the HQ of Cn of holomorphic functions on Cn is zero as well. Okay, which is now an interesting fact, because if you were to prove this directly, this looks pretty hard. If you remember, if you actually go back to the old definition, it would mean that for every cover, you would need to prove that, if you take something in each cover, I mean, doing this constructively looks very hard. But now, thanks to the Dolbeault cohomology, we can easily study this cohomology here. So now we have this nice info. This is some extra info. And where have we seen this sheaf of holomorphic functions? Well, of course, we've seen it in many places, but probably one of the favorite places where we saw it is the exponential sequence. So we use this info on the exponential sequence. So we're trying to use this on the exponential sequence on Cn. So what do we get? Well, we get that the Picard group of Cn, which, okay, we know is nothing but the H1 Cn of O Cn star. It's isomorphic to the H2 Cn Z. And so this we know from the exponential sequence, right? Because here on the left, we would have the H1 of Cn O, which is 0. And here we would have the H2 of Cn O, which is 0. Okay, so we get an isomorphism. But we know also that this H2 of locally constant functions, this is 0 as well. This is direct. And so what it means is that every line bundle on Cn is trivial. Okay? We're just saying the Picard group is trivial. So line bundles on Cn are trivial. You cannot make a complicated line bundle on Cn. They all look trivial. Which is, I believe, is a very interesting fact, because we're talking about line bundles are holomorphic objects. And sure, Cn is contractible, is star-like, is everything you want, but we know that holomorphic objects, it's somewhat weird that holomorphic objects look at the topology. Let's say that. Okay. That's what I'm trying to say. Because everything started by the fact that Cn is star-like, and therefore this is 0, and so this is 0. So these are isomorphic, and this object here is completely topological. I mean, okay, it's the cohomology of a sheaf, so we don't know technically it's topological, but you did some singular cohomology, and this is actually isomorphic to the singular cohomology group of Cn, which is a completely topological invariant. Okay, so we're only looking at topology, but this tells us that some holomorphic objects are always trivial. So this is something deep, I believe. And, we explored the connection between line bundles and divisors, for instance. Let's also look at that. So we take an effective Cartet divisor. defined by a cover U alpha of Cn and some functions fj, which are now just holomorphic because it's effective, no? It's an effective divisor. Such that we know this fj case are never zero, and fj over fk is fjk on uj intersect uk. Okay. And we know that this defines a bundle, and we know from before that this is a trivial bundle. So fjk define a trivial bundle. And what does it mean to define a trivial bundle? Means that there exists some never zero holomorphic functions, gj, on uj, such that gk over gj is equal to fjk, so fj over fk on uj intersected uk. But now we can move gj on this side and fk on this side, and we get that fj gj, which we'll just name fj tilde, it's equal to fk tilde, which is nothing but, of course, gk fk. And in particular, the zero set of fj tilde is the same as the zero set of fj, simply because gj is never zero. So the fj tildes define the same divisors. Define the same divisor, D. But this equality, fj tilde equal fk tilde, tells you that this glue to a function f tilde. So this means that every divisor D, every effective divisor, every effective divisor D is represented by f tilde, which is global holomorphic on Cn, by an f tilde. Every D has its own. Yeah? Because remember, so this is, I mean, the important fact here is that normally divisors are only locally defined as zero holomorphic functions. Here we have something extra, thanks to the fact that every line bundle of Cn is trivial, is that all these divisors are actually defined globally. So there is a function which is zero on them. And in particular, this means that every time you have as a regular submanifold, so if Z is a regular submanifold of Cn, there exists a holomorphic function such that Z is globally defined as f equals 0. Yeah. So I believe this is also an interesting result because a regular submanifold is something, again, which locally is the zero holomorphic functions. And now we get that in Cn, at least, you're globally the zero holomorphic function, which actually helps a lot in many cases. We also, yeah.
Yeah, but does it have to be only one f or?
No,
like,
no.
is
Of course, you can multiply.
Okay, yeah.
You can multiply by any non-zero function, and you get the same divisor. No. So it's the same here. So you know here there exists some GJ which are stars such that blah blah blah, but of course these GJs are not unique. So constantly these f tildes are not unique.
Yeah. Okay.
But of course any two functions defining the same object need to differ only by something which is never zero, right?
Yeah.
differ in the sense of multiplication. So
Originally, I meant is Z of codimension 1 or
yes.
okay,
Yes.
yeah. It's also yeah. Good.
Sorry. Yes, of course. Yeah, Dragon Sumo codimension 1. Is this true for no? I mean, because we no then it I think is not true anymore. Pretty sure it's not true anymore.
Hmm?
Because then I mean, if you were maybe to go for codimension 2, I think if you want to try to follow a similar strategy, you would say okay, codimension. So you have the idea maybe is that you're globally defined as the intersection of two zeros, right?
Yeah.
That's what
Yeah.
you might want. So I would say okay, you take one of those functions and you know that this works, right? Because we have dimension 1. And then on this Z, on this particular Z, you would have a submanifold of codimension 1.
Yeah.
And you would want to prove that submanifold of codimension 1 of this Z also have this property. But to do that, you would need this whole machinery, which I think is simply not true for a different manifold, which is not Cyan, because
Yeah. Because
star-like. But why would this be star-like? Why would this be even simply connected?
yeah.
So yeah, I believe that for dimension 2, at least not for these reasons. But I'm pretty sure, yeah, in dimension 2, you actually have to ask locally. But don't take my word for it. Another place where okay, divisors, right? Another situation where we saw divisors, of course, in the exact sequence defining divisors. So one other thing we have is that if you look at the sheaf of divisors, so global section of the sheaf of divisors, this is going to be isomorphic to global meromorphic sections, functions on Cn, modulus never zero, holomorphic functions on Cn. And why is this? Because the map that goes from H0 of the divisor into H1 is the zero map, because H1 this is just holomorphic. We can do this because H1 of Cn, sorry, this is O star. O star Cn is zero, because this is the Picard group, yeah? So this is the Picard group, it's zero because we saw it. So if you look at the long exact of the short exact sequence defining the sheaf of divisors, then you take the associated long exact sequence, and what you would get is zero, this object, this object, this object, then zero again. Therefore, you have this isomorphism. Yeah. So not only effective divisors are represented globally by holomorphic functions, but every divisor is defined by a global meromorphic function. Yeah. So just take, a representative. Okay, any questions so far?
No, I must think about the last sentence, but no, that's good.
Okay.
Yeah.
So now we're finally ready to prove that the Picard group of CPN is Z. But unfortunately, to do that, we will have to cheat. So we have to give a few facts about the cohomology of CPN, which we will not prove. So HP CPN of Z is Z when P is even and less than N. I mean, not P, but 2K is less than, K is less than N, and is zero otherwise. while the one with coefficients in CPN in holomorphic functions is C over P equals 0. So we're just saying that holomorphic functions CPN are just constants, which is easy because CPN is compact. Otherwise, it's 0 for P greater than 0. Okay, so these are just facts. I'm not claiming that I'm going to give you proof, but maybe let's just have a few observations here. So in this first one, this P equals 0 is easy. And I hope you agree, because H0 of CPN holomorphic functions is just all holomorphic functions CPN. And you should know that holomorphic functions on a compact manifolds are just all constants. The reason for this is the maximum principle, if you've never seen it before. So if you have a compact manifold, the holomorphic function must have a maximum, but holomorphic functions which have a maximum are constant. Have you ever seen this? Okay.
Yeah, no, I have. But that also explains the 0 in higher dimension, doesn't it?
This one?
Yeah, or?
Why?
Let me see the complex again. Maybe I'm. No, I think I messed up the definition of delta now.
Because now if you think, maybe you're thinking of Dolbeault, right?
Yeah.
And then you're like, oh, but if my coefficients are holomorphic functions, then somehow this should get 0. But remember that these are locally holomorphic functions. Yeah. So in principle, those are just sections of a bundle, and this bundle is non-trivial. So you have to pay a bit more attention.
Okay.
I actually don't have a good reason for you to tell you why this is 0. I suppose you compute the Dolbeault cohomology explicitly. So you do actually find, direct primitives. But actually do not know. Well, this one, here you use the fact, which again we didn't prove, that this cohomology in the sheaf, this sheaf cohomology with respect to the sheaf of locally constant functions, which are integers, is the same as the singular cohomology, which you told me you know.
Yeah. Just we don't mean the singular cohomology when we write that, do we? But
no, here we mean here maybe I should put CPN. When we write this, we mean the cohomology of CPN with respect to the sheaf of locally constant functions, which are integers.
Okay.
But this is isomorphic. It's the same. It's the same as a singular cohomology. So you people don't bother. You just write this, and all the cohomologies are the same.
Okay.
And maybe when you studied singular cohomologies, you actually did this. You proved this, maybe. Hopefully.
Yeah, we computed it, but I forgot the.
But the idea is to use the fact that CPN is a CW complex.
Yeah.
You saw,
yeah.
So yeah, CW complex, and you have one cell of dimension 0, no cells of dimension 1, one cell of dimension 2, 0 cells of dimension 3, one cell of dimension 4, and that's where you get this.
Yeah.
So yeah, if you know some singular cohomology and you accept the fact that this is isomorphic to the singular cohomology, then you know this one. This.
Okay.
Okay, so what does this fact give us? Well, this gives us the Picard group of Cn is precisely Z. Because this is the H2 of CPN of Z. Yeah. And yeah, this is from the exponential sequence, yeah? Because you get zeros on the side, and then between the H1 O star and H2 of Z, you get an isomorphism. And so this isomorphism is not just any random isomorphism, but it's the first rank class. Morphism is given by C1, the first Chern class. Okay. So finally, this implies that these bundles here that we saw at the beginning are all the line bundles on CPN up to isomorphism, of course. And we actually get something extra about these bundles. So remember that O1 is also O of the divisor given by the hyperplane. Then O1 admits a global holomorphic section. Global holomorphic section S. And this is the one such that H is S equals 0. Yeah. And therefore, O to the K as S tensor K as a global meromorphic section. Meromorphic section. And I'm taking meromorphic because I'm taking K to really be, it can be negative, okay? And it's holomorphic if K is greater or equal than 0. So what this means, again, from one of the theorems we saw yesterday, is that the map going from global sheaves, global section of the sheaf of divisors into the Picard group is surjective. Yeah, if you remember, we said that the line bundles which are in the image are precisely the one that emit a global meromorphic section. Yeah? This was one of the theorems. So the fact that every line bundle emits a global meromorphic section means that this map is surjective. Okay, this is actually something we already saw that this OKs at the global meromorphic sections with the same method. But the thing we didn't know at the time was that these OKs were all line bundles. Okay.
Yeah, yeah.
And I guess this also comes for free because H1 of CPN. No, this we don't know. Sorry, because the next one would be H1 CPN or M star, and with M star we don't know anything. Okay. So to conclude, we'll go back to exact sequences of vector bundles.
Okay.
So we have F, E, G, an exact sequence of vector bundles. On some manifold M. And we call the sequence, like the whole thing, by cursive S. It's a cursive S, my best cursive S. Okay, what can we do with it? Apply hom G dot. And we know this is an exact functor. Remember, maybe you're confused. Oh, was it an exact functor? It is not for sheaves, but it is for vector bundles. And here you have precomposition by alpha. Then you have GE. And here you have precomposition by beta. And here you have homomorphism from G to G. Okay, so this gives a long exact sequence. So this gives a long exact sequence for the corresponding sheaves of sections. Yeah, so you have three vector bundles. You take the sheaves of sections. We know that this is still a short exact sequence of sheaves, and therefore we get a long one. And in particular, we have the most important, interesting map is always the one that goes, the one given by the snake lemma. So we call it delta, and it goes from H0. So global sections of homomorphism from G2 itself into H1. And theorem. This is the so-called A invariant of the short exact sequence. So A of S, we define it as the image of the identity. So of course, this is homomorphism from G to G. In particular, the identity is a global section. It's a homomorphism, so the identity is one of them. And the theorem is that this sequence splits if and only if this A invariant is equal to 0. Okay, so again, we're linking old properties. So for instance, the fact that a short exact sequence splits with, let's say, new properties. So properties of the cohomology. So let's prove this, maybe on a new page. So let's start in this direction. So we assume that the thing is 0. So we know that the sequence is exact. So hom GE is precomposition by beta H0M hom GG. And here we have our delta map H1M hom GF. It's exact. Then this thing is 0, right? The identity is 0 if and only if it's in the image. So if there exists a G in here, such that beta compose G is identity. But we know that this is equivalent to saying that the sequence splits. Yeah, because remember, the sequence splits means that there is a map from E to F, which is basically the inverse of alpha, but this is equivalent to say that there's also a map from G to E, which is basically the inverse of beta. So that's what we get. Okay. The opposite direction, if S splits, then there exists as the G. Exists a G such that beta compose G is the identity. But then this means that the identity is in the image of this precomposition, but this is equal to the kernel of delta. So this invariant is 0. Okay. There's a corollary for this, just a small observation at this point, is that if this is a short exact sequence, short exact, such that the H1 of M GF equals 0, then it always splits. Splits. But this is a sheaf sorry, the sections of, so we remember when we wrote this, what we meant is the sheaf cohomology, where the sheaf is the sheaf of sections of this bundle. So if you just consider smooth sections, this is always 0. So extra corollary, the sequence always splits in a smooth way. Yeah. The proof of this is the sheaf of smooth sections of Hom GF is a infinity module and it's acyclic. Okay, so this last thing also showed us that every time you have a short exact sequence, where is it? Yeah, a short exact sequence of vector bundles, then this always splits in a smooth way. I mean, splitting in a smooth way, meaning that this, this inverse maps are smooth. Otherwise, you can think, so another thing which was equivalent to saying that the splits is to say that E is just the sum of F plus G. Sure, but the isomorphism, it's only smooth. So if this were for instance, holomorphic vector bundles, then you don't have always that this splits with holomorphic maps. It always splits smoothly, but maybe not holomorphically. Okay, which of course makes then the theory of bundles and cohomology sheaves much more interesting when you're looking at holomorphic stuff. So you have a bit more rigidity. So this concludes today's lecture and the theory for the course.